Hello and good afternoon. The Public Outreach and Education Committee of the Astronomical Society of India welcomes you to the discussion series Ask an Astronomer. I am Sarita Vik, and joining me in the organization today are Professor Mamta Gulati, Dr. Crispin Karthik, and Virendra Yadav from ASI POEC. Our eminent astronomer today is Professor Kuntal Misra from Aryabhatta Research Institute of Observational Sciences, Nainital, and the theme for discussion is gamma ray bursts. Professor Kuntal will be giving a short presentation which will be followed by a discussion. I invite our participants and viewers to note down their questions in the chat box. I will first introduce our speaker. Professor Kuntal completed her PhD from Aries in the year 2008. Following this, she carried out research as a postdoctoral fellow in IUCAA and STSCI, USA. She joined Aries as a faculty member in December 2012. Her main areas of research are high-energy transients, mainly gamma ray bursts, supernova, and electromagnetic counterparts of gravitational wave sources, and big data from survey telescopes. She is the PI of the International Liquid Mirror Telescope at Aries, which is a joint collaboration between India, Belgium, and Canada. It is expected to achieve first light at the end of this year. She is a recipient of the Women in STEM Fellowship of the Indo-US Science and Technology Forum. May I now request Professor Kuntal to begin her presentation.
Thank you, Sarita, for the introduction. I will start sharing my screen now. Please let me know if it's visible.
It's visible.
I've made it full screen now. Can you see the slide in full screen mode?
Yes.
So good evening, everyone. And thank you to ASI POEC for giving me this opportunity to talk about one of the most enigmatic cosmic explosions in the universe, known as the gamma ray bursts. To begin with, as Sarita mentioned, that I work in Aries. Aries is located in the picturesque location of the Nainital hill station. We have another location 60 kilometers away from Nainital, which is known as Devasthal. And it hosts the largest telescope in India, which is the 3.6 meter Devasthal optical telescope. So in future, as and when the opportunity arises, I would like to request all of you to visit this beautiful place and see the night sky using this hill station in Nainital as well as in Devasthal. So my main research interests are in a variety of cosmic transients, but today I'll be speaking about gamma ray bursts. I have kept the talk at a very basic level. So just imagine if you could see something in the universe which is exploding and it's emitting as much energy as nearly the entire universe would emit in just a few seconds. And the amount of energy emitted is typically of the order of 10 to the power of 51 ergs. Not only that, this explosion is so enigmatic that all of the world's greatest observatories would start looking at this object. When I say all the observatories, it means that it is emitting the radiation in all the wavelengths across the electromagnetic spectrum, right from high energy gamma rays to the low energy radio bands. So you would be most likely seeing a stellar explosion. The two biggest explosions which we've seen after the Big Bang are the supernova explosions and the gamma ray bursts. Just to give an analogy between what a supernova and a gamma ray burst is. So supernova word has been derived from the Latin word nova, which means new, and super means awesome. So when we see a new supernova in the sky, which means we are seeing a new awesome transient source in the sky. On the other hand, gamma ray bursts are sudden intense flashes of gamma rays. That is why we call them as gamma ray bursts, because they are coming from the bursts of stars and emitting intense flashes in the gamma ray bands. However, the supernova are very frequent. We typically see around 10 supernovae exploding every second in the universe. On the other hand, there is only typically around 1 GRB which is detected every day. On the other hand, the supernovae in a galaxy like ours, the Milky Way, the number is around 1 to 2 per century, which is very, very rare. The very closest supernova in our nearest neighboring galaxy, the LMC, was 1987A, which was about more than 30 years back now. Not even 30, about 40 years back. And GRBs, on the other hand, if occurs in a galaxy like ours, which is the Milky Way, the rate is very, very small. It's very rare that a GRB would occur in a galaxy like ours. So typically, these GRBs would take around 10 to the power of 4 to 10 to the power of 6 years to be seen in a galaxy like ours, the Milky Way. So the rates of these cosmic transients is very small.
Yeah, I think.
Yeah, same here. I think there is some internet issue at her side.
Mhm.
Just call her and check.
Yeah, I think there's some issue. Maybe we'll just.
Yeah, she's back. She's back.
Okay. Kuntal, probably you can start from that last slide. You are muted. I think you were disconnected also for some time. You are muted. Please unmute, Kuntal.
Can you hear me now?
Yeah.
Okay, I'll start from this slide only. So I'll give you a brief idea about the explosion energetics.
You need to share again.
It's not shared?
No. I think you had got disconnected, so that's
I
why.
got disconnected probably.
Yeah.
Okay, so the energetics involved in these explosions are typically of the order of 10 to the power of 51 ergs in the case of a supernova explosion, whereas in the case of a gamma ray burst. Sarita, you were saying something? Okay. Whereas a gamma ray burst emits energy of the order of 10 to the power of 53 ergs, which is about 100 times higher than that seen in a supernova explosion. The energy emitted from the sun is typically 3 times 10 to the power of 33 ergs per second.
So, excuse me, Kuntal, I think there's a echo somewhere. Is that right? No, that's fine. That's fine. Go ahead.
Can others hear me clearly?
Yeah, we can.
Okay. So if sun has to emit this much of energy of 10 to the power of 51 ergs, it would require about 5 billion years, which is 5 times 10 to the power of 9 years. Which is why these are the magnificent cosmic explosions seen in the universe. Now, during the Big Bang, only light elements were formed, like hydrogen, helium, and lithium. So where are we getting the heavier elements from? The calcium which is present in our bones, or the aluminum which is used in our day-to-day lives in making vehicles or any other things. So these heavy elements are usually coming from the explosions in the universe, like the supernova explosion, because the massive stars have the heavier elements in the form of an onion shell structure, which is the different elements in the star, and these are formed during fusion. And these explosions are also the fundamentals of creation. If you can see from this figure over here, that most of these heavier elements, the green one, the elements which are labeled with the green color, they are coming from the exploding massive stars. And that is why they are studying these explosions in the universe are of fundamental importance to us. I will move on to the transients, which are known as the gamma ray bursts. Why do we need to study gamma ray bursts? The first important aspect would be that they are an indirect clue to the stellar evolution. What kind of stars give rise to GRBs? And in which galaxies do these bursts occur? And indirectly, what can we know about the processes that are going on when a gamma ray burst occurs in any of the galaxy? However, it is also related to the larger picture of the universe, where we can get an indirect evidence about the star formation rate of the universe. And they can be used as cosmological probes in cosmological studies. I will discuss what are the milestones that have been achieved so far in the study of GRBs. So these were detected in the late 1960s by the US Vela military satellites. And this was a serendipitous discovery. It was not a targeted discovery. It was found that these are short intense pulses of gamma rays, typically ranging from keV to MeV ranges, and they last for a very few seconds. These are non-repetitive in nature, coming from random directions in the sky. So the figure which I am showing on the right shows the distribution of about 3,000 gamma ray bursts, which were detected by the BATSE satellite. It can be seen from this figure that they do not have a preferential location, whereas they can be located anywhere and they can come from any random direction in the sky. As they are isotropically distributed, they are located at cosmological distances. And the redshifts that we know for the known GRBs so far, the range of the redshift is from 0.008 to 9.4. So the nearest GRB known to us is located at a redshift of 0.008, whereas the farthest GRB known to us is at a redshift of 9.4. Because they are lying at cosmological distances, they have huge energy output, ranging between 10 to the power of 48 to 10 to the power of 54 Earths. And this is directly related to the energetics of the burst. When I say the redshift of these gamma ray bursts, how do we measure the redshift of GRBs? So the redshift measurement is usually done from the spectrum. The spectrum can be from the afterglow or from the host galaxy. I will define these terms after a few slides. So the figures on this slide show the spectrum of typical gamma ray bursts, where the y-axis is the flux and the x-axis is the wavelength. So by the presence of the emission or the absorption lines, we can estimate the redshift of the gamma ray bursts. Now, we already said that these bursts are isotropic in nature. We typically see one burst per day, but these bursts are highly variable in nature. The light curves of no two GRBs are similar, which means there is no similarity. When you look at the burst phenomenology of a number of gamma ray bursts, then you see that they have varying profiles. They can either be a single pulse, they can be a single pulse, which is typically a broad pulse, they can be multiple pulses, they can be pulses which are very, very narrow, which means they are very short-lived. So this indicates the highly variable nature of gamma ray bursts, indicating that there is no similarity between any two GRBs. There are predominantly two classes of gamma ray bursts, the short burst and the long burst. So the figure on the lower right over here shows the hardness ratio and the T90 distribution of the GRB. So I would like to focus only on the distribution of these dots on this figure, where you clearly are able to see two classes of GRBs. The ones which have a duration greater than 2 seconds fall in the category of the long GRBs, whereas the GRBs which have a duration of less than 2 seconds fall in the category of short gamma ray bursts. Similarly, the figure on the top shows the histogram, and this also indicates a bimodal nature of the gamma ray bursts, indicating two distinct classes of GRBs. When there are two distinct classes of GRBs, there have to be two different models of origin giving rise to these two different classes of GRBs. When the host galaxy observations of these two classes of GRBs were made, they lie in different kind of host galaxies, which again hints towards different progenitors giving rise to these two classes of GRBs. Now, these short GRBs, for which the duration is less than 2 seconds, they also have a hard spectrum, whereas the long GRBs, for which the duration is greater than 2 seconds, they have a soft spectrum. So they are generally known as short hard bursts or long soft bursts. Again, in the case of long gamma ray bursts, we have seen that they are associated with a core collapse supernova. And there has been no supernova association seen for a short gamma ray burst. However, for a short gamma ray burst, in very recent observations, we have seen a kilonova emission, which is coming from the R process nucleosynthesis of the neutron-rich material. The different evidences seen in the light curves or the spectrum of short and long gamma ray bursts have time and again indicated different progenitors or the different formation channels for these two classes of GRBs. Long GRBs, they are typically found in star-forming galaxies. They are close to the bright UV regions of the host galaxy. Whereas the short gamma ray bursts can occur in both late and early type galaxies, and they have relatively larger offsets. When I say relatively larger offsets, it means that they occur away from the host galaxy. So here in this picture, I have shown the typical host galaxies of the long gamma ray bursts, which are generally star-forming irregular galaxies, and the short gamma ray bursts can occur in a star-forming galaxy. It can also occur in an elliptical galaxy. And when I say relatively large offset, so if you see the blue picture of the host galaxy over here, so the galaxy is over here, whereas the crosswire here shows the location of the burst. So this has been seen from very deep observations with the Hubble Space Telescope, and a detailed morphological study of the host galaxies and the locations of the gamma ray bursts in these host galaxies has been performed. Now, when we talk about two different classes of gamma ray bursts, the long and the short, we are directly hinting towards different progenitor channels which are giving rise to these two classes of GRBs. Either ways, there is a collapse taking place, which is leading to the formation of a black hole or a magneton. They can either come from the collapse of a massive star or from the merger of two compact objects. In one of my previous slides, I had shown that the long gamma ray bursts are associated with a supernova, which means, which has an indirect evidence stating that long gamma ray bursts are coming from the collapse of massive stars, whereas the short GRBs are thought to be coming from the merger of two compact objects. It could either be a merger of two neutron stars or a merger of a neutron star and a black hole. And this was recently established by the gravitational wave detection in the year 2017 with the event GW 170817, and the associated short gamma ray burst 1708-17A. This is by far the best observations taken so far for any short gamma ray burst and the gravitational wave signal. And this has put strong evidences to date about the short GRBs coming from the merger of two compact objects. So what happens is that you have, in the case of a long gamma ray burst, if you see the figure on the left panel of this figure, you have a long gamma ray burst, which is a burst that has a duration of greater than 2 seconds. A massive star, the core of the massive star collapses, and the material is expelled out. There is a supernova explosion also. The central remnant object would be a black hole. And there is an accretion disk formed from where jets would be launched. And this causes the gamma ray burst. Similarly, in a short gamma ray burst, you have two compact objects which are spiraling inwards and eventually colliding. Again, when they collide, there will be a central black hole formed. And again, the scenario would be the same as a long gamma ray burst, where the accretion disk formed from the jet formed would give rise to the jet, and which would eventually result in the formation of a gamma ray burst. So there are strong evidences for the two different progenitor channels seen for the long and the short classes of gamma ray bursts. Now, how do we explain this? Once there is a central compact object, the accretion disk has formed and jets are launched. So those jets are traveling through the ambient medium. Only when those jets are directed towards the line of sight of an observer, we will be able to see that gamma ray burst. So the most promising model to explain this scenario is known as the GRB fireball model. And this is also one of the most simplistic models that has been developed, where the burst takes place over here, releasing energies of the order of 10 to the power of 51 to 10 to the power of 54 Earths. Then the material comes out and it is interacting and colliding. There is shock formation. The internal shocks over here in this region, they are giving rise to the burst. And this is where we are seeing the burst photons in the gamma ray energy band. Now, as the ejector slows down, it interacts with the surrounding local or the ambient medium. And once this interaction takes place, so this is these are the external shocks over here. When these external shocks interact with the ambient medium or the surrounding medium, they give rise to an afterglow. And this afterglow radiates across the different wavelengths of the electromagnetic spectrum, right from X-rays to radio to optical, via the synchrotron radiation process. Now, there are different energetics involved in the burst. So when we are detecting the burst photons, we are basically measuring the fluence. To calculate the total gamma ray isotropic energy, we just do applying this, we know the fluence, so we just do 4 pi dl square times the fluence, and that will give you an estimate of the total gamma ray isotropic energy. The second important factor over here is collimation, the collimation angle theta, which I'll come to later in after a few slides. So clearly, as you can see from this figure, there are two phases. One is the burst phase and one is the afterglow phase. There are clear differences between the burst phase and the afterglow phase. The burst phase typically follows a band function. This is just an empirical power law function to the spectrum. And this is the typical prompt energy spectrum, which we see in the case of gamma ray bursts. And these are two power laws. And where these two power laws join, this is the peak energy of the prompt emission seen in a gamma ray burst. However, The afterglows are long-lasting counterparts. As I said earlier, that the afterglows emit across different wave bands of the electromagnetic spectrum. So this is typical afterglow seen in the optical bands. So this afterglow, this GRB happened on 29th March 2003. I will just mention over here the nomenclature. When we say 030329, it means this burst occurred in the year 2003 in the month of March and on the 29th day of March. So the first image, which was taken a few days after the burst, and this is the optical counterpart of this GRB seen in the optical wavelengths. And about a month later, this was still visible, but it had significantly faded. So the fading nature indicates that the afterglows fade over time. Again, I mentioned that these are long-lasting, low-frequency counterparts seen across different wave bands of the electromagnetic spectrum. In one of my earlier slides, I had mentioned that the gamma ray bursts are located at cosmological distances, and the nearest redshift, nearest GRB is located at a redshift of 0.008. If you convert this was typically at a distance of 37 megaparsec. And these are the conversions which I have just put down here for your ease. And when you convert this to the light travel time, it means that the light travel time corresponding to a Z of 0.008 is about 0.112 giga-year, which means that the burst took these many years, the radiation from the burst took these many years to reach us. However, the high redshift GRB, which is at a redshift of 9.4, is 98963 megaparsecs away from us, and the light travel time is about 13.2 giga-years. It means it took this much of time, the light or the radiation from this gamma ray burst took this much of time to reach us. So these are the two examples, the two typical examples of the radiation arriving us from the GRBs, which are located at two different redshifts, the nearest and the farthest gamma ray bursts known so far. The afterglows, they follow a non-thermal spectrum where f nu is directly proportional to nu to the power of minus beta. And this is a general afterglow spectrum which is constituted of broken power laws at different regimes of the electromagnetic spectrum. When we talk about the light curve of an afterglow, as you can see in this figure, the x-axis is time and the y-axis is flux. When the flux is plotted against time, we see that the flux generally fades with time. In some cases, it can be rising also and then fading, but generally, in majority of the cases, we see a fading flux from an afterglow, from X-ray, radio, or an optical afterglow, and which indicates that this is a time-varying light curve where f nu is directly proportional to t to the power of minus alpha, where alpha is the decay index with which the light curve is decaying or falling. Now, when we have introduced these two terminologies about the burst and the afterglow, as we also saw in the fireball model that there were two distinct boundaries for the burst phase and the afterglow phase, there are differences between the burst and the afterglow phase. So the burst phase would see emission only in the gamma ray band, whereas the afterglow is a multi-wavelength phenomena where the radiation is seen across different bands of the electromagnetic spectrum. The burst is very short-lived, of the order of a few seconds. Sometimes it can also be a fraction of a second. Sometimes it can go up to thousands or 2,000 seconds, but generally not more than that. So these are the burst phase is very short-lived. The afterglow is a long-lived, longer wavelength counterpart, and the afterglows can be seen right from 1 day to a few days to a few years. It also depends upon the nature of the burst as well as the band in which we are observing. The burst phase will give you an estimate of the prompt emission and the isotropic gamma ray energy. The afterglow phase, as I said earlier also, is a non-thermal synchrotron radiation. It indicates time-varying flux. At typically 1 hour after the burst, we have seen afterglows ranging from 16 to 24 magnitudes in the R band. They follow a power law decay index where F nu is directly proportional to T to the power of minus alpha. And one very important estimate that can be made from the afterglow is to estimate the redshift of the burst, the redshift at which the burst was located. So this is again done from the spectroscopy or sometimes indirectly from the photometry also. But this is why the afterglows are so important. We can only study the afterglows because the bursts are very short-lived. We really cannot study them for a very long time or observe them for a long time and extract information out of it. But since these afterglows can be seen across different bands and also for a longer time, we have to follow each one of these dedicatedly to actually see the history of the burst or the progenitor star which has given rise to this or any gamma ray burst. Now, we already saw in the fireball model and even during the progenitor scenario that once the accretion disk is formed, jets are launched, which means that the GRBs are highly beamed and they have opening angle of a few degrees. As you can see from this figure, this is coming out in the form of a narrow conical beam, and this is the opening angle which we estimate indirectly. And once this opening angle we call as theta j, this is expanding. The material is expanding and it's coming outwards. As this theta j, it falls or it becomes less than 1 upon gamma, where gamma is the Lorentz factor. One thing which I forgot to mention is that initially during the burst phase, the Lorentz factor is very, very high. These are highly relativistic events, and the Lorentz factor is of the order of 10 to the power of 3. So once the ejector has slowed down and the jet opening angle, it falls below 1 upon gamma, the observer is located somewhere over here. The observer will be able to see larger fraction of the emitting surface. When the observer sees larger fraction of the emitting surface, then the flux drops. And when the flux drops, this is seen as an achromatic jet break feature in the light curves. When I say that this is an achromatic feature, it means that it will be seen at the same time at all bands of the electromagnetic spectrum. And this time at which this flux dropping occurs is known as the jet break time. Now, these jet break times are very important to estimate the energetics of the burst. Primarily, they can estimate the extent of collimation. So with the information of the jet break time, we can calculate this collimation angle theta j, as can be seen from this expression over here, that theta j in a constant density medium is directly related to the jet break time. The other inputs are the redshift, the isotropic energy, and the number density. I won't go into the details of this. On the other hand, if you have an estimate of this Tj, so if you look at this figure over here, here the histogram of the distribution of the isotropic gamma ray energy is shown. In the top panel, you see that E gamma iso, it varies from roughly around 10 to the power of 52 to 10 to the power of 54 ergs. However, if you correct it for the collimation angle theta j, then these bursts have collimated corrected energy typically around 10 to the power of 51 ergs. This picture looks very simplistic, that for all GRBs, if we can estimate the jet break time, we will indirectly know about the collimation and hence we can estimate the true energetics of the burst. The true energetics meaning the collimated corrected energy. But this is not always true. It is now with the detection and discovery of more and more gamma ray bursts, we are seeing the absence of achromatic jet breaks. There are different behaviors seen in the X-ray and the optical light curves. As you can see in the two figures on the right over here, that this is a very bumpy light curve. It shows a flaring nature, it shows a plateau. It doesn't show any feature of an achromatic jet break. Similarly, in this figure, these are the two light curves in the optical and the X-ray bands. Both of them behave differently. So the main criteria to estimate the jet break time is that it has to be achromatic, meaning occurring at the same time at the different energy bands. So as more and more complexities were seen in the light curves, it became very difficult to estimate the true energetics of the bursts. So this poses a very important question about the energetics, about how the energetics can be calculated in such a case and how and whether they can be trusted or not. A similar behavior was also seen in very high energetic GRBs, which were detected by the Fermi Large Area Telescope. So Fermi operates in the waveband, in the energy band of 20 MeV to 300 GeV. The red triangles over here show the most energetic GRBs which were ever detected by the Fermi Large Area Telescope. And none of these energetic GRBs have actually shown a break. So how do we calculate their true energies? In the recent times, we have also seen GRBs which have emitted in the very high energies. We know 3 GRBs so far which have VHE emission detected. I will just talk briefly about one of them, GRB 190114C, which is located right over here. The isotropic energy of this burst was about 3 times 10 to the power of 53 erg, whereas the E peak was around 1000 keV. And the VHE emission for this GRB was detected by the MAGIC telescope. So you can see from this figure that this again lies towards the very high energetic GRBs. There was a multi-wavelength campaign for this gamma ray burst because this was the first ever GRB detected with sub-TeV emission. And in this figure, the light curve or the evolution of flux with time at the entire electromagnetic spectrum is shown, ranging from TeV bands to GeV bands to keV in the X-rays and the optical and the radio bands. So this was one burst, and this is one burst so far, which with TeV emission detected and sub-TeV actually. The highest energy photon detected in this GRB was around 300 GeV, and it was very well followed up with about 24 telescopes across the world. Okay. The 3 primary instruments or the missions which are detecting the GRBs and giving us the localization of gamma ray bursts till date are today, which are operational today. I have not listed the ones which were operating earlier. The main is the SWIFT gamma ray burst mission, which has 3 instruments on board: BAT, the Burst Alert Telescope, which operates in the energy band 15 to 150 keV and is primarily responsible for detecting the gamma ray burst in the gamma ray bands, the X-ray telescope operating at 0.2 to 10 keV, and the ultraviolet optical telescope operating in the ultraviolet and optical bands 170 to 650 nanometer. And this is the mission which gives us precise locations of about a few arc seconds that can be followed up with the ground-based telescopes. The Fermi Gamma Ray mission has 2 instruments on board: the Large Area Telescope, operational between the energy range 20 MeV to 300 GeV, and the Gamma Ray Burst Monitor, operational between 8 keV to 40 MeV. And our own Indian multi-wavelength observatory, the AstroSat, it has 5 instruments on board, but the primary one, which is detecting the gamma ray bursts, is the cadmium zinc telluride imager, which is a coded mask detector, which operates in the energy range of 10 to 150 keV. So these 3 instruments give us information about the gamma ray bursts which are occurring in the sky, and one or another gamma ray burst would be occurring right now in the sky. And if any of these instruments picks it up, we will get an alert that a gamma ray burst has gone off at such and such location. However, once the burst phase is over, we really need to follow the afterglow in the different bands of the electromagnetic spectrum. And India plays a very crucial role in observing these afterglows at the optical bands. As you can see from this figure over here, there are some telescopes marked at different locations around the globe. And why India plays a critical role is that it is exactly in the middle of the 180-degree wide longitude band between Eastern Australia over here and the Canary Islands. So when the observations are not possible at these 2 places due to nighttime hours, can be successfully carried out from India. And we have been studying gamma ray burst afterglows from India for the last 2 decades. And in many cases, we have reported the earliest discovery or the earliest observations of the optical afterglows of gamma ray bursts. And different telescopes are used to monitor the optical afterglows in India. And these are the prime telescopes which I have listed over here, which are used for monitoring the optical afterglows of gamma ray bursts. These gamma ray bursts are also observed at other wavelengths, particularly with GMRT at the radio wavelengths below 1.4 gigahertz. And AstroSat, I already mentioned earlier that AstroSat, the CZTI imager on AstroSat is also detecting the gamma ray bursts. I would like to end my presentation over here and would like to point out that GRBs are not very simplistic in nature. Each GRB poses a challenge to the standard model. I presented some of those complexities in the light curves, especially related to the energetics of the bursts, and whether there could be any alternate methods to estimate the true energetics of the GRBs. And this is still a growing field with the discovery of new GRBs. And in the recent times, with the discovery of the association of the short gamma ray bursts with the gravitational wave detection has opened a completely new window, as well as the detection of the very high energy emission seen in gamma ray bursts has also opened a new window in the electromagnetic spectrum to study these gamma ray bursts. So thank you for listening to this. I'm open to any discussion and questions.
Thank you, Kuntal, for explaining about these gamma ray bursts. Maybe, perhaps we can begin discussion amongst ourselves. Can you hear me?
I can hear you. I
Yeah.
just thought the screen share is
Yeah, that's fine. So I was just wondering that these events you do not know beforehand where they will occur, right? So just for the curiosity of the people who are participating, how do the observers know where, for example, or even the telescopes that are operating, how is it known that a GRB is there in a certain direction, because you are not looking in all the directions at the same time, for example? So how are we able to first detect these events at all?
Yeah. So the primary detection in the gamma ray bands is coming from Swift or Fermi or AstroSat in some cases. These are large area detectors. The Burst Alert Telescope or the gamma ray burst monitor on Fermi are large area detectors which are covering a huge portion of the sky. They are satellites going around and covering a huge portion of the sky. And if they detect anything which is above their energy threshold, they're operating typically in the energy band, which is about 150 keV or more than 150 keV. So if they pick up any signal which is greater than their threshold, They have some onboard algorithms where they process the data and localize whether it is a burst or not. And they will give you a precise location of whether the area and declination of the burst. And once the satellite has confirmed the nature of the burst or whether it is a burst or not, it'll give information to a gamma ray burst coordinate network. There is a gamma ray burst coordinate network which is operational throughout the globe, and it disseminates information to the community. And that's how we know that a gamma ray burst has taken place. And this is all very, very rapid. A burst being detected by a mission and the information reaching us sometimes happens in just a few seconds.
I see. But some of the bursts, as you said, the long gamma ray bursts, they last till a few tens of seconds. Is it possible for the other instruments to catch up also?
Yes, what happens in SWIFT is that because SWIFT has two other telescopes, the XRT and the UVOT, which are co-aligned. So once a burst is detected by BAT, it'll give information to XRT and UVOT, and these two instruments would co-align in the direction of the burst. Because BAT is a large area detector, but UVOT and XRT are also in the same field of view, but not necessarily exactly at the same position where the burst has been detected. So these will co-align in the direction of the burst. And if there is a new source, like in UV or in optical or in X-rays, you can easily identify a new source, which is the afterglow, right? And that will refine the coordinates, the array and deck of the burst. And we are given actually very precise coordinates. The coordinates which are given to the community are very, very precise, coming from SWIFT UVOT, just about with an error bar of around a few arc seconds, just 2 or 3 arc seconds in most of the cases.
Okay, thank you. Are there any questions from Mamta, Virendra, or
I would
Chris?
like to ask something. Is there any typical time difference that is happening between the main burst and the afterglow that we observe?
Yeah, so it depends upon. So when I said that the duration of the burst, which is primarily responsible for classifying the GRBs, the long ones lasting for 2 seconds, for greater than 2 seconds, and the short ones lasting less than 2 seconds. So this 2 second or the burst duration is calculated from the burst phase in the gamma ray band. Okay. So once that burst phase is over, you will start to see the afterglow.
That's like preceded immediately after the burst.
Immediately after the burst, and in some cases, afterglows. It's not necessary that afterglows would be detected in all gamma ray bursts.
Okay.
But in majority of the gamma ray bursts, about 80% gamma ray bursts have an X-ray afterglow. About 60% have optical afterglow, and only about 30% have radio afterglows.
Okay, so any specific reason for not seeing afterglow in almost 20% of the...
Yeah, so it could be that suppose in X-rays it was detected by some other mission which did not have, like if Fermi detects, and if SWIFT is not looking in that direction, then Fermi usually requests a TOO to SWIFT. And it may take time to execute the TOO. So sometimes you may miss the X-ray afterglow. In optical, generally it is thought that suppose we are not in, our telescopes are not able to observe at that location. Or they could be very, very faint for our telescopes or for the existing optical telescopes that we have. Or it could be lying in high dense regions with very high extinction, and which is why the optical afterglows could be obscured and we are not able to look for any optical emission from those.
Okay, so it's more related to the observational restrictions
biases,
rather than any physical phenomena happening.
Yeah. Okay, right.
Fine. Okay, and one more thing I want, since Sarita pointed out the discussion regarding the alerts and how do we get the alerts and all that for the burst happening. Are there any false alert also that happens?
Very few. they retracted immediately. Very, very few.
Okay. Okay.
The number is very less.
Yeah, I think I'm over to you, Sarita.
Okay.
May I ask?
Yeah,
Kuntalji?
go ahead.
Yeah. So, Kuntalji, when you mentioned about the long GRBs, that these are mainly originated from collapsing stars, and then short GRBs, they are occurring mainly because of the merger of, say, two neutron star or a neutron star and a black hole. So, is it possible that, or are there any such mergers where one component was a white dwarf and the other was, say, a neutron star or a black hole, which resulted in a GRB?
The only evidence we have is from the merger of two neutron stars from the gravitational wave signal GW170817. We have not seen any associated counterparts or the electromagnetic counterparts from a neutron star or a black hole merger so far.
Okay.
So there is only one clear-cut observational evidence.
Okay. So, but then what are the other possible origins for, say, short GRBs?
Neutron star, black hole, or two neutron stars are the proposed scenarios for the merger of compact objects, as mergers of compact objects giving rise to short duration gamma ray bursts.
Okay. And where you had mentioned about the distances, so you had mentioned the redshifts, and then you had given the equivalent distance. So, like the nearest one was, I think, around some 37 megaparsecs, something like that.
Yeah.
So, any specific reason, like because that distance is, although it's not very large distance astronomically or cosmologically speaking, but still, it's quite a big distance in which there must be quite many galaxies. So, what is the reason behind GRBs occurring so far away?
Yeah, so these, again, I did not mention one thing, that the high redshift scenario is mostly for long GRBs.
Okay.
What has been observationally seen so far is that the short GRBs are lying at lower redshifts, because they are also thought to be coming from the mergers. So these neutron stars would be more in nearby globular clusters, and these are the primary locations of neutron stars, right?
Okay.
Whereas the long GRBs are coming from the collapse of massive stars and star forming. Their origin is in star forming galaxies.
Mm-hmm.
The short GRBs median redshift is only around 0.5, whereas the median redshift of long GRBs is around 2.5.
Okay, so can I? Yeah,
sure.
Mamta.
Yeah. Kuntal, at this point, can you please put some light on the mass limits of the stars that are forming long and short GRBs?
Yeah, so short GRBs are coming from the compact object mergers. In one case where in GW170817, where the two neutron stars merged, there the neutron star masses were calculated from the gravitational wave signals. They were around, the lower one was around 1.1 solar mass, and the higher mass neutron star was around 1.6 or 1.7 solar masses. Mm-hmm. And typically the long gamma ray bursts, they are coming from stars which are massive and have masses greater than about 20 solar masses. It could be even more, even higher, around 40 solar masses.
Okay, so typically like an order of magnitude difference is there in their masses?
They're completely different, right? One is...
Yeah. At 10 times, that's what I'm saying.
So normally core collapse occurs for stars which are greater than 8 solar masses, and that's how core collapse supernovae also originate.
Right.
But the mass limit of GRBs coming from collapsers is much higher than the normal core collapse events, the normal core collapse supernovae.
Okay.
So we can easily, say that they're coming from stars which are more massive than 20 solar masses for long GRBs.
Okay, and is there any distinction between them based on the type of stars, like O-type stars or type 3?
They are generally Wolf-Rayet stars, massive Wolf-Rayet stars. WR stars are one of the main primary, thought to be the primary progenitors of long gamma ray bursts.
Okay. Yeah.
So maybe we will take up the questions that were asked by our participants from Zoom. Rohit Mandal wants to know, he says that low metallicity stars being progenitors of long GRBs has a massive explosion similar to supernovas. How are they so bright than supernovas? Can we know previously if a star will go off in a GRB or supernova? If yes, then how?
Okay. So I will answer the first part before. That long GRBs are coming from massive star from mass. I just answered this question actually when Mamta asked that GRBs are coming from much more massive stars as compared to supernovae. They are not coming from stars which are of similar mass as the core collapse supernovae, and which is why they are brighter than supernovae, and they emit much more energy as compared to the normal core collapse supernovae. And the other thing is that these are highly relativistic events. So all massive stars cannot give rise to GRBs. Okay, they have to be special kind of massive stars which are rotating, lying in low, having low metallicity to conserve the angular momentum. Only those stars would give rise to gamma ray bursts. All right. So that is the first part of the question, that why GRBs emit much more energy as compared to supernovae. And if we can know previously whether a star will go off in like a GRB or a supernova, it's very, very difficult to know because we have so many massive stars in the universe. And to track the evolution of each of those massive stars is not a very easy task, I would say. So it is rather impossible to know beforehand which star would become a GRB or a supernova. However, in the recent times, there are groups who have undertaken projects to map the massive stars to the stellar deaths. I am not very clear about that, but to my understanding, there is no prior way to know which star will immediately go off, or should we be looking at, we will have a rough idea when we know the evolutionary stage of a particular star, we will have a rough idea, but we cannot precisely say that today this star would go off and give rise to a GRB or a supernova.
Okay, so the next question is by Rayat, who wants to know, he says the energy released has to go through the interstellar medium and many energy loss phenomena to reach our detectors. Then how are we estimating the high energy released initially?
So there are two different things actually, because these bursts are occurring at cosmological distances, which means it is an external galaxy. So we are not dealing with ISM there. We are not dealing with the interstellar material there. We are dealing with the circumstellar material there. And as soon as the burst goes off, once the burst goes off, we are detecting the gamma ray photons, which are being captured by the space telescopes. Okay, so the burst photons are being recorded by the space missions, where there is no attenuation going on due to the circumstellar material or the interstellar material at a very later stage once it is reaching us. Those sort of effects would only affect the afterglow, not the initial prompt emission. When the gamma ray photons have been recorded by the missions, you can directly convert it using 4 pi dl square times the fluence. So what the detectors are recording is the fluence, which is erg per centimeter square per second. So if a burst has a typical fluence of 10 to the power of 6, 10 to the power of minus 6 erg per centimeter square per second, you can calculate the gamma ray isotopic energy, which is E gamma iso. It's nothing but just summing around the 4 pi spherical area, the 4 pi dl square times the fluence.
Okay, so the next question, there are a couple of questions by Churchill Trivedi. The first is, you highlight the cause of large GRBs to be hypernovae, but what causes the generation of this tremendous amount of gamma ray photons in the progenitor in the first place? And what special scenario is happening over there?
Yeah, so these are very highly relativistic events. When the gamma ray burst occurs, the Lorentz factor is very, very high. These are rapidly rotating stars which are giving rise to gamma ray bursts. And once this explosion takes place, it emits in very high energies. And because of the very high Lorentz factor involved, the internal shocks are created. The shells are moving outwards. The faster moving shells, they will slowly catch up with the shells in the outer regions of the ejecta. And once that happens, it gives rise to the internal shock. And in this internal shock scenario, because the photons have a very high energy and they are highly relativistic in nature, we are seeing the very high energetic photons over here. Once the ejecta cools down, and this is also the optically thick phase, this phase is around the burst is the optically thick phase. Once the ejecta cools down and enters the optically thin regime, we are able to see the less energetic counterparts, which are known as the afterglows.
So the second question is, how far do you think primordial short GRBs due to binary neutron star or neutron star black hole mergers could help in probing the very early universe? And what idea about the before burst central engine can be obtained from the observed GRB data?
To be honest, I don't know the answer to the first part, because short GRBs are only a handful so far, and the only confirmed case of its actual association with a compact object merger is from the gravitational wave signal. So I will not attempt to answer the first part of the question. I will attempt to answer the second part of the question, which is about the idea before the burst central engine can we get from the observed GRB data. Yes. So once the burst goes off, all the information is lost. What we have recorded is the gamma ray flux or the fluence, okay? And then we are observing the afterglow. So what we have recorded is the afterglow. We try to construct a SED from the observed data and fit that SED to the different galaxy models, different stellar population models, and try to estimate the star formation rate, and hence infer the different what kind of stars would have given rise to such a to any particular burst. So it is like backtracing the history of the progenitor star and the burst from whatever observations we have taken in the afterglow phase.
So those are the questions from Zoom. Mamta, are there any questions from YouTube participants?
Yeah, there's one question. Some of them are already answered by Kuntal already. So there's one question that is not answered yet that says that, is there any difference between the duration of afterglows for a short GRB and a long GRB?
Yes, there is. I forgot to mention that. So short gamma ray burst optical afterglows typically fade very rapidly, and they are also fainter as compared to the afterglows of long gamma ray bursts.
What about the intensities of the intensities of the gamma ray bursts themselves?
That also is relatively weaker in the case of short gamma ray as compared to long GRBs.
Okay. So it will be anyway difficult for us to be able to observe them if they are coming from very far or very distant.
Yeah, but short GRBs are typically lying at lower redshifts.
Yes.
So we should be able to see them more if the relative intensity of the gamma ray photons was the same.
Mm-hmm.
But the gamma ray emission itself in short GRBs is weaker as compared to long GRBs.
So are they, Mamta? Yeah, go ahead.
That's all about the questions from YouTube as of now. I would like to ask one question at this stage. That is there any the afterglow is coming because of the interaction with the medium also, for example, like you have a shock front that is created and there's another burst and you see an afterglow, that in the uh, diagram that you showed. So is there any pattern that we see in the intensity of the afterglow, if there's any other interaction happening with maybe like a shock front and again creation of a shock front at a later stage?
Yeah, so what I presented was a very simplistic picture of internal shocks giving rise to the burst photons, and the external shocks when interacting with the surrounding medium giving rise to the afterglow emission, which is radiating via the synchrotron process. There also could be inverse Compton effect, but that is not seen very frequently.
Okay, so I asked this question for the very simple reason that if there are any bursts happening in a region where there is a lot of extinction, so can the interaction with the medium of the burst photons be observed in some other by some other means, like you just now mentioned, inverse Compton or radiation or something else? Is why I asked this question at.
Yeah, if it is anyway happening at a very in a region which is at very high extinction, the optical afterglow would certainly be obscured.
Yeah.
It would be very, very difficult to detect it in the optical bands. But in X-rays, that won't be the case. If there is a detected X-ray afterglow, so sometimes these GRBs are also known as dark GRBs. There is a class of GRBs which is known as dark GRBs, where there is an X-ray afterglow detected, but there is no optical afterglow detected, which means it is dark in the optical. And this is one proposed scenario for a dark GRB, that it could either be lying in a highly extincted region, or it could be like very, very far away, which we are, and outside the capabilities of the observational facilities that we have.
Okay. So the high redshift GRB limit 9 point something that we have observed.
9.4,
yeah. Is it has to do with the early formation of galaxies also?
Yeah. So that is it's occurring in the early universe, and that redshift has been estimated using photometry. It is not a spectroscopic redshift, but a confirmed spectroscopic redshift at 8.3 has been estimated for a long GRB.
Okay. Okay. Yep. That's all from my side and from the YouTube questions, Sarita.
Yeah. So thanks, Mamta. And I think we will now be closing. We are at the end of this session, and we thank Professor Kuntal for giving an insight into the phenomena of gamma ray bursts. To summarize, Professor Kuntal explained about the types of GRPs, the nature of emission and progenitors, giving rise to these different types, and also giving us an overview about the different instruments and the satellites which are carrying out these measurements. On behalf of ASI POEC, we thank you. We also thank our participants in Zoom and YouTube for participating in the program. Thank you very much.